There is something strange happening far beyond Neptune, something we cannot see, but we can measure. Not a planet, a black hole, not the kind that swallows stars, not even the remnants of a dying sun. Something much smaller, roughly the size of a bowling ball, yet with the mass of 5 Earths silently orbiting our own star. It sounds impossible, but the gravitational evidence is real. And now NASA, along with multiple research teams around the world, is taking this idea seriously. This is a dwarf planet, a small, icy world orbiting in a region of space far beyond Neptune. Its closest approach to the Sun is about 80 astronomical units. That's 80 times the distance between Earth and the Sun. To put that in perspective, Neptune orbits at about 30 AU. Pluto, at its closest, comes in at around 29.6 AU. So VP 113 is way out there. It's in what astronomers call the inner Oort cloud, a region so distant and so poorly understood that we're still trying to figure out what's even out there. But the weird thing about 2012 VP 113 isn't just its distance, it's the shape of its orbit. This object follows an extremely elongated path around the Sun. At its farthest point, it swings out to about 452 AU. At its closest, it's still 80 AU away. That's unusual. Most objects in the solar system have more circular orbits. But what's really strange is that 2012 VP 113 isn't alone. There's another object called Sedna, discovered back in 2004. Sedna has a similarly extreme orbit. Its perihelion, or closest approach to the Sun, is 76 AU. Its aphelion, or farthest point, is an astonishing 937 AU. These two objects are what astronomers call sednoids. They're part of a group of extreme trans-Neptunian objects, or ETNOs, that orbit far beyond the influence of Neptune's gravity. And here's where it gets interesting. By 2016, astronomers had identified 6 of these ETNOs with orbits that shared something peculiar. Not only were their paths stretched out and distant, but they were also aligned with each other. Their perihelia, the points where they come closest to the Sun, were all clustered in roughly the same direction in space, and their orbital planes were tilted at similar angles. This kind of clustering shouldn't happen by chance. Over billions of years, the gravitational influence of the known planets should have randomized these orbits, scattering them in all directions. But that's not what we see. Instead, these objects are moving as if something massive and unseen is shepherding them into similar paths. Astronomers calculated the odds that this clustering was just a coincidence. The result? About 0.007%. That's roughly 1 chance in 15,000. So either we're witnessing an extraordinarily unlikely coincidence, or there's something out there that we haven't discovered yet. Something with enough gravitational influence to shape the orbits of objects billions of kilometers away from the Sun. In January 2016, 2 astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, published a paper that offered an explanation. They proposed that a massive planet, somewhere between 5 and 10 times the mass of Earth, is orbiting the Sun at an extreme distance. This hypothetical world would have a highly elliptical orbit, with a perihelion around 280 astronomical units and an aphelion that could stretch out to 1,120 AU or more. It would take this planet somewhere between 10,000 and 20,000 years to complete a single orbit around the Sun. If it exists, this would be the 9th planet in our solar system. A true planet, not a dwarf planet like Pluto, something massive enough to dominate its orbital region and clear out any debris in its path. Batygin and Brown called it Planet 9. The idea wasn't entirely new. Astronomers have been speculating about undiscovered planets in the outer solar system for more than a century. But this was different. This time, the evidence was stronger. The clustering of the ETNOs was statistically significant, and computer simulations showed that a planet with the right mass and orbit could explain not just the clustering, but several other oddities in the outer solar system. For example, Planet 9 could explain why some objects are on orbits that are nearly perpendicular to the plane of the solar system. It could explain why certain high-inclination trans-Neptunian objects exist at all. And it could explain the orbits of objects that cross the paths of the giant planets, but somehow remain stable. The hypothesis made sense. It fit the data, and it gave astronomers something concrete to search for. But there was a problem. Planet 9, if it exists, would be incredibly difficult to find. At such an extreme distance, it would reflect very little sunlight. It would be faint, dim, and moving slowly across the sky. Searches were launched using some of the most powerful telescopes on Earth, including the Subaru telescope in Hawaii. Astronomers scanned the regions of the sky where Planet 9 was most likely to be, but so far, nothing has turned up. By 2021, Brown and Batygin had refined their predictions. They accounted for observational biases and reanalyzed the data. Their updated estimate placed Planet 9 at a distance of about 380 AU, with a mass around 6.2 times that of Earth. Still, the planet remained elusive. Some astronomers began to question whether Planet 9 existed at all. Maybe the clustering was a result of observational bias. Maybe we were only seeing a small, unrepresentative sample of objects, and if we found more, the pattern would disappear. Others proposed alternative explanations. Maybe a passing star had disturbed the orbits of these objects long ago. Maybe there was a disk of smaller bodies out there, massive enough to create the clustering through their collective gravity. Or maybe, some researchers suggested, it wasn't a planet at all. Maybe it was a black hole. When we think of black holes, we usually think of two kinds. The first kind is the stellar mass black hole. These are formed when massive stars run out of fuel and collapse under their own gravity. They typically have masses between about 3 and 20 times that of the Sun. The second kind is the supermassive black hole. These are the giants that sit at the centers of galaxies, including our own Milky Way. They can have masses, millions, or even billions of times that of the Sun. But there's a third kind of black hole that's purely theoretical. We've never detected one directly. But if they exist, they could be almost anywhere. These are called primordial black holes. Primordial black holes would have formed in the very early universe, less than a second after the Big Bang. During this chaotic period, regions of space with slightly higher density than their surroundings could have collapsed directly into black holes. Unlike stellar mass black holes, primordial black holes don't have a minimum size. They could be as small as a subatomic particle or as large as thousands of solar masses. The ones that interest us today are somewhere in the middle. We're talking about black holes with masses comparable to planets, Earth mass black holes, or even smaller. A black hole with 5 times the mass of Earth would have an event horizon, the point of no return, only about 5 centimeters across. That's roughly the size of a grapefruit. But despite its tiny size, it would still have the gravitational influence of 5 Earths. It would warp space-time around it, pulling on nearby objects just like a planet would. And here's the key point. From a distance, you couldn't tell the difference between a 5 Earth mass planet and a 5 Earth mass black hole. Not just from their gravitational effects. So when astronomers talk about Planet 9, they're really talking about a gravitational anomaly, something with mass, something pulling on those distant objects. But what if that something isn't a planet? What if it's a primordial black hole that was captured by the Sun billions of years ago? In 2019, 2 researchers, Jakob Scholz from Durham University and James Unwin from the University of Chicago, published a paper exploring this possibility. Their argument was based on 2 separate lines of evidence. The first was the clustering of the extreme trans-Neptunian objects, the same evidence that led to the Planet 9 hypothesis. The second was an observation from the Optical Gravitational Lensing Experiment, or OGLE, a survey that uses gravitational microlensing to detect distant objects. Over 5 years, OGLE detected 6 ultra-short microlensing events. These events lasted only 0.1 to 0.3 days, which suggested that the lensing objects, the objects bending the light, were relatively small. Based on their analysis, Scholz and Unwin estimated that these objects had masses in the range of 0.5 to 20 Earth masses. Now, there are 2 ways to interpret this. One interpretation is that these are free-floating planets, rogue worlds that were ejected from their home star systems and are now drifting through interstellar space. The other interpretation is that these are primordial black holes. If the OGLE events are caused by primordial black holes, then there's a population of these objects in our galaxy. And if that population exists, then it's not unreasonable to think that one of them could have been captured by the Sun. Schultz and Unwin calculated the probability of this happening. They found that the odds of the Sun capturing a primordial black hole are roughly comparable to the odds of capturing a free-floating planet. In other words, if we're willing to entertain the idea that Planet 9 is a captured rogue planet, then we should also be willing to entertain the idea that it's a captured black hole. The two scenarios are equally plausible, and there's an added benefit to the black hole hypothesis. It explains why we haven't been able to find Planet 9. A planet, even a distant one, reflects sunlight. It has a thermal signature. It emits infrared radiation as it cools. With the right telescope, it should be detectable. A black hole, on the other hand, is invisible. It doesn't reflect light. It doesn't emit radiation, except for a minuscule amount of Hawking radiation, which would be far too faint to detect. If Planet 9 is a black hole, then it's essentially undetectable by traditional means. But that doesn't mean it can't be found. If there's a black hole orbiting the Sun, it would be surrounded by a halo of dark matter. Dark matter is the mysterious substance that makes up about 85% of all matter in the universe. We can't see it directly, but we know it exists because of its gravitational effects on galaxies and galaxy clusters. Primordial black holes would naturally attract dark matter. Over billions of years, a black hole would accumulate a cloud of dark matter particles around it, forming what's called a dark matter microhalo. And here's where things get interesting. If dark matter particles can annihilate, that is, if they can collide with each other and convert their mass into energy, then the dense concentration of dark matter around a black hole would produce a detectable signal. Specifically, it would produce high-energy gamma rays. These gamma rays could be detected by space-based observatories like the Fermi Gamma Ray Space Telescope or future telescopes like the Vera C. Rubin Observatory. In 2020, researchers Amir Siraj and Avi Loeb proposed another detection method. They suggested that the Rubin Observatory could search for flares produced when objects, like asteroids or comets, fall into the black hole and are torn apart by its gravity. These flares would be brief, lasting only a few hours or days, but they would be bright enough to be visible from Earth. Another possibility is to look for the black hole's gravitational influence on known objects in the solar system. For example, if a black hole with 5 times the mass of Earth is orbiting at several hundred astronomical units, it would slightly perturb the orbits of the giant planets. Jupiter, Saturn, Uranus, and Neptune would all be tugged by its gravity. These perturbations would be small, only a few meters over the course of an orbit, but they might be detectable with precise measurements. Some researchers have even proposed launching a fleet of small spacecraft toward the outer solar system. These probes wouldn't need to reach the black hole. They would just need to pass near enough to detect its gravitational pull. By monitoring the timing signals sent back by the probes, scientists could measure tiny changes in their trajectories. If the probes were pulled off course by an unseen mass, that would be evidence for a black hole. All of these methods are speculative. None of them have been tried yet, but they show that even an invisible black hole might leave clues that we can follow. Not everyone is convinced by the Planet 9 hypothesis, let alone the black hole hypothesis. Some researchers argue that the clustering of the ETNOs could be a result of observational bias. We tend to look at certain regions of the sky more often than others, and we're more likely to find objects in those regions. If we found more objects in different parts of the sky, the clustering might disappear. In 2020, a team of astronomers analyzed data from the Outer Solar System Origins Survey, or OSSS, which observed over 800 trans-Neptunian objects. They found no evidence of clustering in the orbits of these objects. However, other researchers pointed out that the OSS source sample included many objects that were too close to Neptune to be influenced by Planet 9. When the analysis was restricted to the most distant objects, the clustering was still present. Another alternative explanation is that there's no single massive object out there at all. Instead, there could be a disk of smaller bodies, collectively massive enough to create the clustering through their combined gravitational influence. This idea is called the Zederek-Madigan belt, or ZM belt. It would require about 10 to 20 Earth masses of material spread out in a ring around the Sun, far beyond the Kuiper belt. The problem with this hypothesis is that we haven't found enough objects to account for that much mass, and it's unclear how such a disk could have formed in the first place. Yet another possibility is that the clustering is caused by modified Newtonian dynamics, or MOND. This is an alternative theory of gravity that suggests gravitational forces don't weaken as quickly at large distances as Newton's laws predict. If MOND is correct, then the orbits of the ETNOs could be explained by the gravitational pull of the Milky Way galaxy, rather than by a hidden planet or black hole. But MOND has its own problems. It struggles to explain other observations, like the motion of galaxy clusters and the cosmic microwave background, and it would require a major revision of our understanding of physics. So the debate continues. Some astronomers are confident that Planet 9 exists, others remain skeptical. And a small but growing number are entertaining the possibility that it's not a planet at all. If Planet 9 turns out to be a primordial black hole, it would have profound implications. First, it would confirm that primordial black holes exist. That would give us a new window into the very early universe, when these objects are thought to have formed. Second, it would suggest that primordial black holes could make up a significant fraction of dark matter. If one black hole is orbiting our Sun, there could be countless others scattered throughout the galaxy. Third, it would raise fascinating questions about the history of our solar system. How did the Sun capture this black hole? Was it part of a close encounter with another star system? Or was it captured from the interstellar medium billions of years ago? And finally, it would mean that we've been living in a solar system with a black hole for the past 4.5 billion years, and we never knew it. But we should be cautious. The evidence for Planet 9 is strong, but it's not conclusive. And the evidence for a black hole is even more speculative. What we know for sure is that something strange is happening in the outer solar system. The orbits of these distant objects are telling us a story, but we don't yet know how to read it. Over the next few years, as new telescopes come online and new data becomes available, we'll get closer to the answer. Maybe we'll find a planet. Maybe we'll find a black hole. Or maybe we'll find something we didn't expect at all. For now, all we can do is watch, measure, and wait. This mystery reminds us how much we still don't know about our own cosmic neighborhood. We've mapped the surface of Mars in stunning detail. We've sent probes to the outer planets and beyond. We've detected thousands of planets orbiting other stars. But right here, in our own solar system, there are still secrets hiding in the dark. The outer solar system is vast, cold, and almost entirely unexplored. It's a frontier that's just as alien as any distant exoplanet. And the idea that a black hole could be lurking out there, invisible and silent, is both unsettling and thrilling. It's a reminder that the universe is full of surprises, that even the things we think we understand, like our own solar system, can still hold mysteries. Whether Planet 9 is a planet, a black hole, or something else entirely, the search for it is pushing the boundaries of what we can observe and what we can imagine. And that's what makes this story so compelling. We're living in a moment where we might be on the verge of discovering something extraordinary, something that will rewrite textbooks and change the way we think about our place in the cosmos. Or we might find nothing at all, and the mystery will deepen. Either way, the search continues. And the universe keeps its secrets a little while longer. This isn't the first time astronomers have predicted the existence of an unseen planet based on gravitational anomalies. In fact, this kind of detective work has a long and fascinating history in astronomy. And sometimes, it's been spectacularly successful. The story begins in the early 19th century with the planet Uranus. Uranus was discovered in 1781 by William Herschel, making it the first planet found using a telescope. But as astronomers tracked its motion over the following decades, they noticed something odd. Uranus wasn't moving the way it should. Its orbit deviated slightly from the path predicted by Newton's laws of gravity. Sometimes it moved a little faster than expected. Sometimes it lagged behind. These perturbations were small, but they were consistent. Something was pulling on Uranus, something that wasn't accounted for in the mathematical models. In the 1840s, two mathematicians independently worked on solving this puzzle. Urbain Le Verrier in France and John Couch Adams in England both came to the same conclusion. There must be another planet out there, beyond Uranus, whose gravity was causing these deviations. Le Verrier calculated where this planet should be located. He sent his predictions to Johann Gaillet at the Berlin Observatory, and in September 1846, less than an hour after Gaillet began his search, he found it, Neptune. The discovery was a triumph for physics and mathematics. It showed that Newton's laws could not only describe the motion of objects we could see, but also predict the existence of objects we couldn't, and it set a precedent. If gravitational anomalies could reveal one hidden planet, maybe they could reveal another. After Neptune was discovered, astronomers noticed that Uranus still had some unexplained perturbations. Maybe there was yet another planet out there, even more distant than Neptune. This led to a decades-long search for what was called Planet X. Percival Lowell, a wealthy American astronomer, became obsessed with finding this mysterious world. He established an observatory in Flagstaff, Arizona, specifically to search for it. He made mathematical predictions about where Planet X should be, based on the apparent irregularities in the orbits of Uranus and Neptune. Lowell died in 1916 without finding his planet. But the search continued. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell's observatory, discovered a distant object that seemed to match the predictions. This was Pluto. At first, Pluto was hailed as the long-sought Planet X. But there was a problem. Pluto was much smaller than expected, far too small to account for the supposed perturbations in Uranus and Neptune's orbits. As better measurements came in, astronomers realized that the perturbations they thought they had detected weren't real. They were errors in measurement. Uranus and Neptune were moving exactly as they should, given the known planets and their gravitational influences. Planet X didn't exist, at least not in the way Lowell had imagined. Pluto was demoted from planet status in 2006, reclassified as a dwarf planet, and for a time, it seemed like the era of predicting hidden planets was over. But then came the discovery of Sedna and 2012 VP-113 and the other extreme trans-Neptunian objects. And once again, astronomers found themselves looking at gravitational anomalies that couldn't be explained by the known planets. History was repeating itself. The methods that led to the discovery of Neptune were being used again, this time to search for Planet 9. But there's an important difference this time. Neptune was relatively close, astronomically speaking. It orbits at about 30 AU, and it's large enough and bright enough that once astronomers knew where to look, they found it quickly. Planet 9, if it exists, is much more distant. And if it's not a planet at all, if it's a primordial black hole, then it might be impossible to find using traditional methods. So the question becomes, are we chasing another Neptune or another ghost? One of the most powerful tools astronomers have for testing the Planet 9 hypothesis is computer simulations. These simulations allow researchers to create virtual solar systems and watch how they evolve over millions or even billions of years. They can add a hypothetical Planet 9 with different masses and orbits, then see whether the resulting patterns match what we observe in the real solar system. Konstantin Batygin and Mike Brown have run hundreds of these simulations. And what they've found is striking. When they add a planet with about 5 to 10 Earth masses on a highly eccentric orbit at several hundred astronomical units, something interesting happens. The orbits of the distant trans-Neptunian objects start to cluster. Their perihelia align. Their orbital planes tilt in similar directions. In other words, the simulations reproduce the exact patterns we see in the real data. But the simulations revealed something else too. Something unexpected. Planet 9 doesn't just affect the most distant objects. It also influences objects closer in, including some that cross Neptune's orbit. These objects get kicked into high-inclination orbits, nearly perpendicular to the plane of the solar system. And when astronomers went back and looked at the data, they found that such objects actually exist. There's a population of trans-Neptunian objects with inclinations greater than 50 degrees. They were discovered years before the Planet 9 hypothesis, but no one had a good explanation for them. The simulations explained them naturally. This is what gives many astronomers confidence that Planet 9 is real. It's not just explaining one anomaly, it's explaining multiple, seemingly unrelated features of the outer solar system. But the simulations also have limitations. They assume that Planet 9 is a planet, a solid body with a well-defined mass and orbit. They don't account for the possibility that it could be a black hole or a cluster of smaller objects, or something else entirely, and they're only as good as the data we put into them. If our observations are incomplete or biased, the simulations might be leading us in the wrong direction. That's why the Rubin Observatory is so important. It will give us a much larger and more complete sample of trans-Neptunian objects, and with that data, we'll be able to test the simulations more rigorously. If the clustering persists as we discover more objects, that strengthens the case. If it disappears, then we'll need to rethink everything. There's another possibility we need to consider. What if Planet 9 doesn't exist at all? What if the clustering of the trans-Neptunian objects is just a statistical fluke, or a result of observational bias? What if we've been chasing a phantom? It wouldn't be the first time. Remember Percival Lowell's Planet X, which turned out to be based on measurement errors. Or consider the case of Vulcan, a hypothetical planet that was once thought to orbit between Mercury and the Sun. Astronomers in the 19th century observed irregularities in Mercury's orbit that they couldn't explain with Newtonian physics. They proposed that a hidden planet, which they named Vulcan, was responsible. Searches were conducted. Some astronomers even claimed to have seen it. But Vulcan didn't exist. The irregularities in Mercury's orbit were eventually explained by Einstein's theory of general relativity, which showed that gravity behaves differently near massive objects like the Sun. No hidden planet was needed. Could something similar be happening with Planet 9? Some researchers think so. They argue that if we account for observational biases and use a more complete data set, the clustering of the trans-Neptunian objects disappears. Samantha Lawler, an astronomer at the University of Regina, has been one of the most vocal skeptics. She points out that most of the objects used to support the Planet 9 hypothesis were discovered by surveys that focused on specific regions of the sky. If we only look in certain places, we're more likely to find objects in those places. That doesn't mean they're clustered. It just means we haven't looked everywhere yet. Lawler and her colleagues analyzed data from the Outer Solar System Origin Survey, which was specifically designed to minimize observational bias. They found no evidence of clustering in the orbits of the objects they observed. However, Brown and Batygin counter that most of the objects in the OSOS sample are too close to Neptune to be influenced by Planet 9. The distant objects that do show clustering are rare, and OSOS simply didn't find enough of them to confirm or refute the hypothesis. The debate is ongoing, and it highlights a fundamental challenge in astronomy. We can only observe a tiny fraction of the outer solar system. Most of it is too faint, too distant, or too obscured by the glare of brighter objects. So we're always working with incomplete data, and that makes it hard to distinguish between real patterns and statistical noise. The only way to resolve this is to gather more data, and that's exactly what the Rubin Observatory will do. If the clustering is real, it will become more obvious as we discover more objects. If it's not, the pattern will dissolve as the sample size grows. Within a few years, we'll know for sure. This mystery raises deeper questions about how we understand the universe. For centuries, astronomy has been a process of discovery. We build better telescopes. We look deeper into space. We find new objects, new phenomena, new mysteries. But what happens when we're searching for something that might not exist? What happens when the evidence is ambiguous and the explanations are speculative? This is where science becomes less about certainty and more about hypothesis testing. We propose an idea. We make predictions based on that idea. And then we test those predictions against observations. If the predictions match the data, the idea gains credibility. If they don't, we revise or abandon the idea. Planet 9 is a perfect example of this process in action. The hypothesis makes specific, testable predictions. It predicts the existence of certain kinds of objects in certain kinds of orbits. It predicts that we should find more extreme trans-Neptunian objects with clustered perihelia. If we find those objects, the hypothesis is strengthened. If we don't, It's weakened. But the hypothesis doesn't stand alone. It's competing with alternative explanations. Observational bias, the Zderik-Madigan belt, modified Newtonian dynamics, primordial black holes. Each of these alternatives also makes predictions, and each one will be tested by future observations. This is how science works, not by declaring absolute truths, but by weighing evidence and refining our models. And sometimes, the answer we get isn't the one we expected. Maybe Planet 9 is a planet. Maybe it's a black hole. Maybe it's something else entirely. Or maybe it's nothing at all. But the process of searching for it, of testing the hypothesis, of pushing the boundaries of what we can observe and what we can imagine, is valuable in itself. Because even if we don't find Planet 9, we'll learn something about the outer solar system, we'll discover new objects, we'll refine our models of orbital dynamics, we'll develop new detection techniques, and we'll be reminded, once again, that the universe is full of surprises. The next few years will be crucial. The Rubin Observatory will begin its survey in 2025. Within the first year, it should discover thousands of new trans-Neptunian objects. The clustering, if it's real, will be unmistakable, and the predictions of the Planet 9 hypothesis will be put to the test. At the same time, other searches will continue. Astronomers will analyze archival data from infrared surveys. They'll use precision measurements of planetary orbits to look for gravitational anomalies. They'll monitor the sky for gamma-ray flares that could signal a primordial black hole. And, if we're lucky, someone might actually see Planet 9, or detect the dark matter halo around a black hole, or discover something entirely unexpected. The possibility is real. The tools are in place, and the search is accelerating. But we should also be prepared for the possibility that the answer might take longer than we hope, or that it might not be as clear-cut as we'd like. Science doesn't always move in straight lines. Sometimes the path to understanding is winding, with detours and dead ends. But that's part of what makes it exciting. We're not just searching for a planet or a black hole. We're exploring the unknown. We're testing the limits of our knowledge. And we're asking one of the most fundamental questions in astronomy. What else is out there, hiding in the dark, waiting to be found? For now, the answer remains elusive, but the search continues. And every new observation brings us a little bit closer to the truth.